Yeah, hello and welcome to PML School. In our session today, we continue with our comparisons of non-MEM and NLME models. But as you may know, so far we have only dealt with PK models, so with pharmacokinetic data. And today I will explain how to model pharmacodynamic data. So we are starting with PD models. And the data I'm using today is best modeled with an Emax model. The data is in vitro data. So these are coming from tumor cells from patient samples. And these tumor cells were incubated with a drug. And the cytotoxicity was measured for a certain time. And now the Emax model should be applied which is actually an inhibitory model, and we have a baseline and a shape factor. As usual with our PML School webinars, we will record the session and we will publish this to our YouTube channel. We will provide the materials, the slide deck and the project files, the models, on our forum and our LinkedIn group, our PML School LinkedIn group. So you can download it from there. And if you've got some questions or comments, please feel free to use the Q&A panel on the right-hand side of the WebEx console. Okay, let's move ahead. This is our model, a short description. As I said, it's an Emax model with baseline and shape factor. For the error model, we are using a multiplicative or proportional error model. There are 4 structural parameters to be estimated. Emax, the maximum effect, EC50, the concentration at half maximum effect, slope or better shape factor, and the baseline. Next are our fixed effects. These are the 4 structural parameters, and what's given here is just the initial estimates and the boundaries. And then we've got 3 random effects. Let me see if I can get a laser pointer. 3 random effects, eta 1, eta 2, eta 3. And as an engine, we are using FOC ELS. Okay, very short exploratory analysis. This is a plot of the first patient, so concentration and the effect. So concentration for these PD data sets typically on a log scale. And you see we are starting with some higher density of tumor cells, and this goes up on drug action, it goes down, and maybe reaching 0. So this is an inhibitory Emax model with some baseline shape. You can't see shape here, but this will be estimated by the engine. Typically, we also look at the input data for the models, and typically we would have 2 slightly different inputs for non-MEM and Phoenix NLME, but this is not the case here. This time we are using the identical input for both non-MEM and NLME, and you see already there are lots of columns. I didn't get all the columns on this slide, but most of the columns are covariate information, and we are not using covariates in our model, so we can ignore those. What we need to do is to focus on 3 columns. This is first the ID column that's differentiating between the patient samples, concentration, this is a drug concentration that was applied, and DV, the dependent variable, which is the actual effect. And this we are using for both non-MEM and NLME. So now we are coming to the comparison of the codes. As usual, non-MEM NM-tran code on the left-hand side and NLME PML code on the right-hand side. First thing we specify is the input. It has a dollar input statement for non-mem, and this is actually reading in all the columns from the data set. And what you see in NLME, this is typical for Phoenix NLME. If you're having PD data, you are going to use a covariate statement to read in the independent variable. In this case, independent variable is concentration, and this just links the input to the PD model. But there's also another way you can deal with that, and I'll show that in the demo. Next section is the specification of structural parameters. Here are a few lines of codes in NMTran. You see there's a Emax, which is actually our structural parameter that we define with a fixed effect, θ1. Then we've got a couple of lines. Yeah, this is a mathematical construction that should constrain the effect between, or Emax between 0 and 1. So you first log it, your Tmax, and then you put that into another ilogit statement where you add some between subject variability, like eta1 in this case. And then we've got the other three structural parameters, EC50. This comes with a typical form where you have a fixed effect, θ2 multiplied by the random effect in exponentiated form, eta2. Slope doesn't have a random effect, it's just θ3. And the baseline also comes with a random effect, but this in a different form. It's in the just an additive form, not an exponentiated form. And finally, to express the effect here, you see this is just a Hill equation with the slope and the EC50 included. When you compare this to the right-hand side, to the PML code, this is, I would say, identical. I mean, it's really identical, more or less. And this shows you, I mean, it's very similar. If you are dealing with PD data, you can more or less copy one by one between non-mem and NLME, which is nice. Next one, oops, come on. The fixed effect in the random effect, so theta and omega arrays. This is in NMTran typically an indexed array, θ1, 2, 3, and so forth. And we are only using the 4 thetas for Emax, EC50, slope, and baseline. And it states here the boundaries, between 0 and 1, and the initial estimates for this value is 8. And then also the random effects, the omega array with eta 1, 2, and 3 all set initially to 1. And when you look at the right-hand side, we are using in PML the fixed F statements and random statements. And this is also almost identical. Typically, what I'm using here is to actually use the name of the parameter in the definition of these fixed effects. But I'll this time I stick to the NMTran type of code so that you can see how similar the code really is. And for the random effects, you have the typical random statement with a diagonal block of eta1, eta2, and eta3 also initially set to 1. Next one, yeah, the residual error model. This is, here sigma is set to 1, and the predictor variable y is, calculated by the individual prediction plus the residual error multiplied by a weighting function, and the weighting function is 1 to the y squared, or 1 to the squared individual predictions. And this is a typical proportional error or multiplicative residual error model. This the equivalent description in PML code uses the error statement where we set the initial value for epsilon to 1, and we use the observe statement to say that the dependent variable is just the individual prediction plus the fraction of the individual prediction multiplied by epsilon. Also here you've got some additional lines of code which gives you the expression for the individual prediction, which is base minus base times Emax times E1, IRS, W, and IWS. So this is more or less the code, not too many lines, but it gives you an impression how you can compare these models, the PD models in non-MEM and NLME. With that, I'm coming to the demo. So I'll show you now how to deal with these models in Phoenix. So here's the Phoenix interface. I've already loaded prepared project file. You have the data, the imported data, which I showed you as the input data in the slides. This is the worksheet with all the different columns, lots of covariate information. But here ID, conc, and DV, this is what we're going to use. And then we've got the code. For non-MEM, we've got the control file. And for NLME, we got the PML code. So what you do in order to start modeling is you take your input data and send it to, in this case, we start with non-MEM, the non-MEM shell. I put it just into this workflow. And here it asks for a control file, so you can just drag over the control file from the code folder, and you have the code already here. We don't want time residual plots because we don't have time in our data set. This is the PD data set. We only have concentrations. So this is all you need. I mean, the mapping should be fine. The input is mapped here with all variables linked. Okay, and that is enough. Just you can now start. Oops. I think there was one. The DV variable should be ABS. Yeah, that was this. And off it goes. And then it will launch this job on your local computer. You need to have a local non-MEM installation on your computer. And this will run in a few seconds, already finished. And here you've got the results back. So you've got lots of control files back. Yeah, for example, all the ETAs, the omega worksheet, and theta, the theta values. So we just look at it maybe later on in more detail when we have the NLME data ready. So this is now done for the non-MEM part, and then now let's send this also to a Phoenix NLME model. So we take the Phoenix model object for this. And for the model, we need to change from the built-in options to a textual model so that you can have the text here. And this is just a text editor field or dialog. So I just removed all this code, and I can just copy this from here and paste it into this window. Paste. And here's the code. You see already there's some warnings. Yeah, this is something. This is something that I wanted to talk about. In the PML code that I showed on the slide, I would link in the concentration data through the covariate statement. This is a different thing you can do. You can just specify a dummy differential equation by giving this statement, deriv test equals 0. And this creates a time domain for this model. And then, I just need to map time, conc to time in order to say my independent variable is conc instead of time. It might be a little confusing, but it has some advantages to just do this. And then you see this is the code that we have here, much the same. And we can just give it a start and say execute, and it will run this job as well. So it takes a few iterations, maybe 20 to 30, to come up with the results. And here it is already. So we got a theta worksheet, for fixed effects with the final estimates, standard errors. And the CV percent looks good, confidence intervals look good. Omega table also looks good. You can have a look at some of the plots. The conditional weighted residual histogram looks good. Some diagnostics here and there, all good. But for these comparisons, for these pairwise comparisons, as I showed you in previous sessions, I've created this comparison workflow where you just specify some data links, then you create comparable eta values, residual values, plots, and so forth. And this is all here in some sub-workflows where you can see, okay, here's the theta table, and this is the output. So you have the output from non-mem next to the output from NLME together with the standard errors. The same for eta. There you have here the eta 1, 2, 3 from NLME and from the corresponding ones from non-mem. But also you've got lots of plots. So you can compare the histograms side by side, eta histograms side by side. These look familiar. Also the diagnostics, you can see the diagnostics like the CWRS versus IVA and the same versus spread. Looks very similar, all looks good. Some predicted actual plots, so on the log scale. So this will give you a good information about how close and how similar these results really are. Okay, this is actually what I wanted to show with the demo. So as I said, you can pick up this Phoenix project file from our user forum or from the PML School LinkedIn group so that you can look at it in more detail using more time. I'll stop sharing this one and go back to the slides. So just summarize the comparison between the non-mem and the LME. You know, from the code itself, it was already a high similarity, but also when you look at the outcome, you see highly similar outcome results. The spaghetti plots here, the individual predictions and observations against concentrations looks good. Look like also nice fits. So the results are very close, and also from the diagnostic plots that I showed also, these are really comparable results. With that, I guess I'm at the end of the presentation. So I wonder if you've got some questions or comments, then we can have a look at the Q&A panel now. Cheryl, I'm not sure if I see that, but
I do not see any questions or.
Okay. All right. If there are no questions, then you can, if you've got some questions later on, you can send to me at any time, and we can get into a dialogue there. With that, I guess we are already at the end. Very short webinar this time. But before ending, I just want to raise your awareness to our next session. It's been in 3 weeks' time, not in 2 weeks' time. So on June 28th, I will show you another PD model, an indirect response model with an IV bolus dosing, and we go through a similar kind of session. Okay, with that, I'm at the end. Thank you for your continued interest, and looking forward to see you in the next session. And goodbye, and you may disconnect now.